Thank you. It's a great honour to be here, and I thank the organisers and thank Ian for the ability to come and give a talk today. I'm going to give a brief introduction to my research, or a little bit of a summary of my research, and then a quick talk on the synthesis of a little fungal metabolite that we have been involved in. So I'm from Adelaide. This is actually the third time that I've been had the privilege of talking at one of these events, and indeed I talked about how Ian rang me at home when I was madly writing my PhD in my 50-50. I talked about the first chemistry that we did in the 60-80 as a little introduction. Today I'm going to give you a little history of my work that's really been inspired by Ian's synthesis of polyketide natural products, and I will proceed. So let's start with a couple of pictures of Ian. This is actually a picture, and hopefully people can recognise themselves in this slide. This is actually the first group picture we had. There's me, Ian as a young man, and lots of people here from Roger, etc. So there was also the following year, so there's some other characters here. Richard looking, I think, about as young now as he did then. So and Jonathan Goodman in the background there. So that was the actual group at that time. There's a couple of ones here with partners. They're slightly blurred. This was back in the day before real photography. This is a scan from an actual slide. So there's a couple of little bits and pieces here, and I won't talk too much about those. But the group was great fun in the day. Right back in the day, the group was great fun. I did see reference to the trip to Alton Towers outside in the book as well. So this was Ian at Alton Towers and a friend. I don't know if we should tell Nina about that, but it's a long time ago now. So, and we went to conferences. So there's Alison and Roger and Ian and Julian as well from back in 1992. I've got a few more slides at the end as well that I might show if ever I get through the talk. Okay. I have an interest in polyketide synthesis of small natural products. I have run quite a small group in Flinders for a reasonable length of time. We all know that the polypropionate biosynthesis involves formation of the linear carbon chain with alternating oxidation and alkylation along that chain. And depending on the enzymes that are present, you can have hydroxyls, alkenes, carbonyls, or just completely saturated species. I've certainly had an interest in the actual, I've had an interest in this post-chain extension structural features in terms of the novelty of the compounds that you can produce by the cyclization or the subsequent cyclization of those species with things from hemiacetals to dihydropyrones to spiroacetal dihydropyrones and pyrone species. And we've had an interest in the synthesis of all these compounds with the usual determinations of structures and conformation of stereochemistry, etc. The cyclization modes are interesting. You can think about the linear precursor can form the hemiacetal. That hemiacetal can subsequently dehydrate to give the dihydropyrones, and as Jonathan alluded to with his synthesis of dolibriferol, you can actually have that hemiacetal do retroclason process, and we've investigated all those types of processes. Now, just a little bit slow. So I won't talk in too much detail about any of this chemistry except one little bit that is the furanylidene natural products. But this compound that we did synthesize a while ago, oripyrone, is an interesting one because the linear precursor has a degree of symmetry where one side actually forms the pyrone and the other side actually forms the spiroacetal dihydropyrone. And indeed, in that process, we made a linear precursor like this where we'd pre-established the pyrone, but in fact it cyclised in the wrong way. So this is certainly something you always have to think about with these compounds, that they potentially can do different processes. We actually did do this total synthesis of this compound via making the spiroacetal portion first and building on the actual pyrone at a late step, which has been published and I think is an interesting bit of chemistry that we did do. Now, there it is. What's it doing? Oh no. Oh, there it is. Okay. So, it's pretty bad if it collapses on me. No. So, at any rate, we also just mention here a compound that we had an interest in, tridacylhydropyrone, and we were able to complete the synthesis of this compound as reported in the structure. And it's an interesting one because it seems to be the result of an electrocyclization of the precursor compound, where the carbon-carbon bond is formed in an electrocyclic process. It turns out that the reported structure was actually trans, but it turns out we made that compound not via this type of process. That was a bit of a different chemistry, but indeed we were actually able to show that that's not the stereochemistry for that particular compound. Okay, I'll talk a little bit for a minute or two about these gracilio ethers. These compounds, I actually talked a little bit about some of our initial chemistry towards these at the previous 60-80 symposium, and this chemistry we've subsequently published and finished this chemistry a few years ago now. So this chemistry involves the formation of this furanylidene via a cascade process, or it's believed to form from these cyclic peroxides that are also known natural products in a non-Delaunay type rearrangement process, where the oxygen to oxygen bond cleaves and you get a cascade cyclization to form the furanylidene. And indeed, the actual synthetic approach that we used for these compounds is very much based on that strategy, in that we generated an appropriate precursor. This is the fragment of the molecule here. We produced that by alkylation and asymmetric dihydroxylation in a quite nice little short sequence here, and we were able to do the condensation of that with the dianion of lithium-sodium dianion, shown here, to give our precursor. And in this quite interesting, I think, transacetylization process, we were able to encourage the compound to do the cyclization and the subsequent double dehydration to give this furanylidene structure. And again, quite a novel feature that's formed from the initial polyketide skeleton, and indeed we were able to take that through to both the gracilio ether B, which is the enone, and also the by selective Nauri reduction to give the gracilio ether C compound as well, and we published that a few years ago. So that's a little rundown on my interest, inspired with Ian in the synthesis of these polyketide secondary structures. I just want to talk very briefly, and this is a short discussion of isolation of a new fungal metabolite, and this is some unpublished work that we have been involved in. I got involved in a project with some mycologists who had a PhD student who was doing extraction of some Australian native fungi. They were looking at this curry punk fungus and doing an extraction of this bracket type fungus. They were able to both extract the wild fungus and also grow it in the laboratory and able to do an extraction of that compound. And this is where my chemistry got involved in terms of identification of this novel structure. There were some previous reports of this compound that had been isolated from the structure, the pigment compounds, by old Mel Gill back in the 1980s, a long time ago. The current extraction varied a little bit in terms of the different solvent that was used, and it was using an antibiotic assay, a simple antibiotic assay, to try and target some antibiotic compounds that were present. And indeed, we ran the NMR spectra of the compound, and in fact, the NMR spectrum of the compound that is shown here appears almost like a fatty acid, and it's almost like the structure you just throw away and think that's not at all interesting. But it turned out that it had 3 carboxylic carbons, 2 quaternary alkenes, as well as the fatty acid alkene. So it did seem to have a fatty acid side chain, but some other functionality as well that was present. And notably, this singlet here at 3.5 parts per million was notable. Now, we tentatively identified the structure, or we tentatively assigned that structure as shown here, where we have this novel, almost new functional group, this tricarboxylic acid with the quaternary double bond and that all-important signal at 3.55 parts per million. Now, I say almost because, in fact, if we searched into the literature and we found that there was one previous report of a structure, and this in fact was done by some researchers, and I mentioned this to Richard, at Merck in the mid-1990s. They actually identified this compound organic acid in Merck, and they were able to determine that particular structure. So this is the only other molecule, natural product, that has this structural feature that was present. And it probably doesn't look too exciting a compound, but we were interested in confirming the structure. We wanted to make sure we had the chain length right and the double bonds, and it's very tempting to do a retrosynthesis where you use oleic acid as a very simple starting material and disconnect at this point. In fact, if you think about the key to the synthesis, it actually becomes a little bit more straightforward if you imagine that instead of installing the double bond initially in this position, you put the double bond here with some sort of Wadsworth-Emmons type chemistry, and then break this down to methyl oleate and this dimethyloxylate as a starting material. The synthesis looks very straightforward, and that looks probably a really nice idea, and it would have been a really great idea if we'd actually had it ourselves, but it's actually based on a patent for a now defunct patent for organic acid that was from about 2011, and they actually used this procedure. So we wanted to apply that to the synthesis of our compound. Could we do that? Yes, quite readily. We could take the methyl oleate and deprotonate, do the condensation. We could do the Wadsworth-Emmons to generate the alkene, and it does equilibrate into the correct position. And the student, this was done by an honours student, actually effectively a Part 2 student, was able to hydrolyse off to give the triacid, and we were able to compare the spectra with the natural product. So certainly we compared the spectra, and there was a really good match for the structure of the natural product. So we confirmed that we had made that compound, and we had confirmed the structure of that particular compound. And we made a couple of analogues. We made the trans double bond for some biological testing, and we also made the saturated compound as well, just to put into the bioassay for looking at the antibiotic activity of this particular compound. And I suppose in some respects this compound is very simple and very straightforward, and if that was all there was to it, I might not have chosen to talk about it. But it does do one other thing that's a little bit interesting and really is quite something that was a bit different, because as we do, we've all done our synthesis and we've isolated compounds, and we're running spectra of different fractions, and one of the fractions that we actually ran the NMR of was completely different to the NMR of fractions of either side, which were the triacid, and it appeared that at least on one occasion the compound had decarboxylated, and so this seems to be a novel decarboxylation of this tricarboxylic acid to give this structure where the methyl group, the CH2, has all but disappeared, and the methyl group now has appeared here at 2.1 parts per million. And indeed, we were able to do that in the laboratory. It turns out that despite the fact that it did it on the rotovap, and it's still a little bit of a mystery how that happened, we needed reasonably forcing conditions with lithium hydroxide at reflux for an extended period to get the decarboxylation to occur, but we could do that quite readily on our synthetic sample. And indeed, this compound was also a natural product, right? So this compound was actually a known compound, and again, that's, I suppose, an interesting thing, because this compound, which had been reported back in the 1990s with this particular structure, was potentially actually an artifact of isolation, and maybe, in fact, the true natural product in that species was the same as our particular structure as well. So that's an interesting, I think, little bit of information there. Now, that's the question: are they artifacts of our compound? Maybe, maybe not. It's certainly a new route to these compounds. Making these compounds is a little bit more difficult than the route that we had at the previous synthesis, and these are still, you know, available for investigation of farnesyl transferase activity. So having a new route to these is somewhat useful. The potential biological activity of our compound I haven't talked about. In terms of the potential biological activity, I haven't talked about, and I'm not sure if they're probably going to be much use beyond maybe as antibacterial soap components or some such thing. Obviously, there's been some patents investigation that have been dropped in the past for certainly that type of compound. Okay, so what have we done? We've done some synthesis. We've made a variety of different compounds. I've talked about the little novel structure that we isolated from that fungal metabolite. List of compounds. We've done lots of synthesis of a variety of these compounds published over the last 20 years. As I said, I've had quite a small research group doing this work, primarily PhD students doing the work, and I would like to acknowledge all those students, and again, it's been great to have been able to be part of their process and moving forward. So thank you for your attention. Happy retirement to Ian. Ian was very good in visiting me many times in Australia, and we've been to many places. This is the Big Lobster, and Ian at the Big Lobster at the Blue Lake. You can see Ian in his element on the beach and on a boat, right? So in various places. Certainly we had the 50-50 celebration and we all looked younger. I certainly looked younger then as well. And the 60-80 celebration. So it's fantastic to be here. Thank you for the opportunity to talk, and I really do appreciate it. And hopefully that's been a reasonable presentation. Thank you.
Don't go away. Stay. Right. So we don't have any Q&A. However, Mike, great talk, fantastic pictures, trip down memory lane, particularly this one here.
That's a photo from the 60-80. I took a photo of the photo that was at the 60-80,
Okay.
yeah.
I think I might have Ian to thank. thank for that one, but I'm not quite sure.
Yeah, so yeah, that's a photo of your of a photo.
We have two Aussie speakers today that have come a very long way to join the symposium. It coincides with me having to give up my college room. And in my college room, I've accumulated various souvenirs of my travels through the years. So it's appropriate to repatriate some of those souvenirs. And what I've got for Mike, which I think is appropriate, because I believe, although I've never run the experiment, if you throw this item in the correct manner, it comes back. So Mike,
Okay.
you'll come back.
Thank you. Thank you, Ian. I'll let the next go, but thank you very much. I really, truly appreciate it. I mean, it is a long way from Australia, and the 2 years with COVID, because quite literally, I think Ian invited, I'm sure he invited everyone to this event, which was meant to be last October, quite literally a month before COVID hit, certainly, it was just 2 years that have been hard, I think, for everyone. So thank you very much, Ian. Fantastic. Thank you.